Today we're going to go a step further with what we've been doing with conductors and insulators and forces and fields, and we're going to talk today about charge distributions. Okay, we talked about what can happen to a conductor. Okay, electrons move around the surface of a conductor because the electrons are fairly free to move about. But what is the distribution going to look like after these charges do move about as a result of forces between each other and so on and so on and so on? Before we talk about this, though, we've got to define a new term. Okay, you guys have heard this term very briefly in Physics 20, but you probably don't remember exactly what it means. That term is static equilibrium. First, let's talk about equilibrium. Okay, you've heard that word in the context of physics, probably in the context of biology and in chemistry as well. What does the word equilibrium mean? Homeostasis, okay. That would be a biology type thing, right? Okay, that works for biology. Balance, somebody said, perfect. Okay, balance is exactly what I'm looking for. When you're talking about homeostasis, you're still talking about balance, right? When you're talking about equilibrium in physics or in chemistry, you're still talking about balance. It's just different things balancing. In physics, equilibrium normally comes from balanced forces. So when we're talking about static equilibrium, we're talking about forces that are balanced. Now, when you have a conductor and you have excess charges on it, you've got, say, 1,000,000 protons, but you've got 1,000,003 electrons. You've got a few extra electrons, then those charges are going to repel each other. Those extra electrons are going to push each other apart. They're going to move all over that conductor until it reaches a point when those charges experience balanced forces. And that's going to be more or less a random process. It's a random process that will happen fairly quickly so that they will reach equilibrium where the forces are all balanced fairly quickly. But it's not instant. Okay, it's a process whereby these charges are going to move around the conductor until they do balance all the forces out. What does the distribution of charges look like when that happens? When they've reached static equilibrium, when they've reached that point where the forces are balanced and the charges are no longer moving. Static means stopped, right? Not moving. What does the distribution look like when the charges have stopped moving because the forces have all balanced? By the way, I made one final comment here. This does not happen in non-conductors. It doesn't happen in insulators. You don't get this charge distribution thing that we're talking about today happening in insulators. How come? Why not? Yeah, the electrons don't move about freely. Now, it doesn't mean you can't have a charged insulator. You can. Okay, if I take a plastic object and rub it against rabbit fur or something like that, or some kind of wool, then it'll develop a charge. But the charge that's on it isn't going to move around that object. You're not going to get this charge distribution like you are in these conductors, because the electrons, once you get that buildup, they pretty much stay where they are. We're going to take a look at several different shapes of objects, and we're going to look at the charge distribution of all these extra electrons, these excess electrons on each of these different shapes. The first one is when we have what we call a solid conducting sphere. Solid conducting sphere is a ball, but it's a conductor. It's kind of like one of those steel marbles. This steel ball, or this solid conducting sphere, has extra electrons on it. Maybe it's got 1,000,000 protons and 1,003 electrons. Maybe it's got 1,000,000,000 protons and 1,003 electrons. Doesn't matter. It's got extra electrons. Now, the electrons that are there balancing the number of protons, that's not the ones we're talking about here. Okay? They're going to be distributed more or less evenly throughout, along with the protons. They're in the atom for the most part. The extra electrons aren't going to be distributed all around. What happens to them? Well, I want to focus on these 3 electrons right now. The same analysis could apply if there was 100 extra electrons or 1,000 or 1,000,000 extra electrons. We just have a more complicated looking diagram, that's all. Let's call this one number 1, let's call this one number 2, and let's call this one number 3. Electron number 1 will experience, as a result of 2 other charges, 2 forces. there's going to be a repulsive force caused by number 2. That repulsive force is going to go this way, away from charge number 2. Does that make sense? You agree with that? Okay, 1 is going to be repelled by number 2, but it's also going to be repelled by number 3. So you get another force up here. What happens to that charge number 1 as a result of those 2 forces? Where's it going to go, Callum? It's going to go in between, right? It's going to go this way. It's going to go towards the surface. Now, what about the other ones? Charge number 2 experiences a force caused by number 1 and a force caused by number 3. Where does it go? It goes out this way. Number 3 experiences a force caused by number 1 and by number 2. It goes outward as well. So the first thing that I want you to observe here is that when you have extra charges in a solid conducting sphere, they will all go to the outside. They will all go to the outer surface of that conductor. It seems a bit weird. There will be no extra charge inside this conductor. They will all go to the outer surface. And they all go to the outer surface because they all push each other to the outer surface. Now, why don't they go beyond the outer surface? Why don't they go off into the air? Like this red force, this red net force acting on charge number 1 here is pushing it out, right? Why can't it keep pushing it out way out here? Well, if it's big enough, it can. But if you've only got a few extra electrons, then the force of repulsion isn't big enough to cause it to leave this conductor and move into air, which is an insulator, right? So what happens? It stops there. Again, if those forces are big enough because you've got so many extra charges, then it can leave the conductor and go into the insulator. But it has to be really, really big repulsive forces. Therefore, you have to have a lot of extra charges, not just a couple. The other thing that I want you to notice about this is that these charges, they're going to the outside, the outer surface, but they're also, if you look at the spacing of them, they also end up being evenly distributed. And that's going to happen every time. If you've got a solid conducting sphere, the extra electrons will go to the outside, and they will be on the outer surface evenly distributed around it, evenly spaced. If they're not evenly spaced, then the forces aren't going to balance. And if the forces, the repulsive forces between them don't balance, it's not going to be in static equilibrium. Does that make sense? So given enough time, and I mean, it's not an instant thing, but it's also not a 5-minute thing. It happens very, very quickly, depending upon the size and so on of the object. And given enough time, these electrons will reach a point of static equilibrium, and they'll do that when they're on the outer surface and they're evenly spaced. Yep. Like an even amount, like 4, 2 or 4? No. No, it would still work. No, the answer to the question is no. It would still work with an even amount of electrons. We could do this with 3, 4, 5, 6, 68 trillion, 148 billion, whatever. It's just the analysis becomes a little bit more complicated. If you've got 4, they're going to be evenly distributed. They're just not going to be evenly distributed at 120 degrees around here, right? They're going to be evenly distributed at 90. So you're going to get one here, one here, one here, and whatever evenly distributed around there is. Make sense? Okay, now you can copy that out. All right, let's take a look at the next shape. Again, I'm going to ask you just to hold off on writing this until I've finished describing it here, okay? I want you to look down to the first diagram here. We see 3 excess charges on this solid, flat conducting plate. There could be a million excess charges. The analysis is exactly the same. It's just the vector diagrams become a little bit more tricky, that's all. The free body diagram, I should say, becomes a little bit more tricky. We're going to call this charge number 1. We're going to call this one charge number 2. We're going to call this one charge number 3. Now, charge number 1 experiences a repulsive force caused by number 2, and it experiences a repulsive force caused by number 3. Both of those forces will cause number 1 to be pushed to the left. That makes sense? 2 pushes 1 to the left. 3 pushes 1 to the left. The net force on number 1 ends up being to the left. Okay, F2-1, F3-1 combined to give me a force to the left. Now, object number 3, or charge number 3, also experiences 2 force. One of them is caused by number 1, one of them is caused by number 2. you can see that that force is quite a bit smaller than the force on number 1. Anybody tell me why? Anybody see why, Jesse, that the force on number 3 is smaller than the force on 1? Well, it's further away from one of them, right? The force of 1 on 3 is the same value as the force of 3 on 1. But the force of 2 on 3 is a lot less than the force of 2 on 1. So that gives us a net force to the right still, but a smaller net force to the right than the force on number 1. Now here's the interesting one, number 2. Let's look at the two forces that are acting on it. Okay, there's the force of 1 on 2 that pushes it away to the right. There's a force of 3 on 2 that pushes it away to the left. Can you explain to me why that force to the left is dramatically smaller than the force that's acting to the right there, Cal? Good. 2 is much further away from 3 than it is from 1. Good. Remember Coulomb's law, F is equal to KQ1 Q2 over R squared. As R gets bigger, F gets smaller. So of course we should predict that force to be a smaller value. All right, what's going to happen? We're not in static equilibrium now, right? Okay, these forces are not balanced. We're not in static equilibrium. What's going to happen to charge number 2? Let's focus on this one. What's going to happen to charge number 2 as a result of those two forces, 1 acting on 2 and 3 acting on 2? Yep. Well, it's going to move to the right, right? The net force on number 2 is to the right, so it's going to start moving to the right. But what's going to happen to the value of F32 as it starts moving to the right? It's going to start getting smaller. What's going to happen to the value of F12? F12 is going to start getting, F32 is going to get bigger. Yes, F32 is going to get bigger, you're right. And F12 is going to get smaller, right? So this force starts getting smaller, this force starts getting bigger, until there comes a point when those two forces are going to be the same values. What happens when those two forces are the same values? It's going to be in that point of static equilibrium now. Where is that going to happen? When charge number 2 gets to the middle. So it's reached static equilibrium once again when these charges are on the outer surface, just like they were with the solid conducting sphere, and once again when these charges are evenly distributed, just like they were with the solid conducting sphere. So if you've got, here's the rule of thumb, if you've got a nice uniform object like a flat conducting sphere or a flat conducting plate or a solid conducting sphere, the charges will always, number 1, go to the outer surface, and they will always, number 2, be evenly spaced. Does that make sense? All right, now you can copy this one down. By the way, one final little thing here. You see these blue lines pointing down towards it. What do those blue lines represent? Those are the field lines, right? We know that field lines point toward negatively charged objects. Why? Well, because they point individually towards negative electrons. All right, let's take a look at this one now. This one is the most confusing of the bunch because this one is irregularly shaped. This one is kind of pointy. The other two we've had have been uniform. It's either been uniformly flat or uniformly curved like a sphere. This one is kind of pointy. Here we've got extra electrons again. There's 4 of them drawn, although the analysis that I'm going to show you is only going to involve 3. Same analysis applies if you have 50 or 500. It just becomes a little bit more complicated, that's all. I want to label 3 of these, 1, 2, and 3. And I want to focus on charge number 2 right now. Charge number 2 will experience 2 forces. Okay, if we're pretending this one's not there. It experiences 2 forces. Yep. The first force is caused by number 1, and it's a repulsive force that's going to go this way. We're going to call that F12 acting to the right. Does that make sense? 2 is pushed away from number 1, so it's going to go kind of to the right. Well, 3 also pushes 2 away, so 3 is going to push 2 up this way. And it's roughly the same value. I should draw that a little bit shorter. It's roughly the same value because those are roughly the same distance apart, give or take. We'll call that F32. All right, and what's going to happen to this charge? Well, what we got to do to see what happens to this charge is look at forces not acting in different directions here, but components of forces acting on one plane. So in other words, what we want to do is look at the x component. We'll call it the x, even though it's not exactly the x-axis. And the y component, even though it's not exactly the y-axis, of F32. The x component of F32 and F12 are going to be what controls where it goes on the surface. The y component is what drives it out to the surface, right? Why does that electron go to the outer surface just like in the other situations? Because the y component of F32 pushes it out to the surface. Once again, they're all going to go to the outer surface. But what's the distribution on the surface look like? 1, 2 is bigger than the x component of F32. What's going to happen to that charge as a result of these two forces right here? Yep. It's going to go to the right, closer to the point, right? It's going to go to the point where F12 gets smaller, the x component of F32 gets bigger, until those forces balance out. That's when it's going to stop. It's going to be in static equilibrium. But because of the irregular shape, and because of the analysis of the component right here of F32, that's going to result in a situation where they're not equally spaced. Rather, they're more concentrated at the tip. You can see in the final diagram, the excess electrons are all over this object, but they're more concentrated at the tip than they are anywhere else. Your finger's an insulator, but it happens to some degree with your finger. You walk across the carpet, okay, you go to shock somebody, you don't stick out your cheek to shock somebody. What do you stick out to shock somebody? Your finger. Why? Because your finger's pointy. Why does that matter? Because there's a bigger buildup of charge in pointy things than there is in smooth things, like your cheek. Does that make sense? We get a higher concentration of charge right here at the end of your finger than we do in other parts of your body that aren't so pointy. Does that make sense? All right. Now you can copy this one down. All right, next shape. Let's see what it looks like. This one's easy because it's the same thing, basically the same thing at least, as a solid conducting sphere. This time this one's hollow though. I'm not going to give you the detailed explanation as to what happens here. I'm just going to tell you the end result. If you've got a hollow conducting sphere, the same thing happens as a solid conducting sphere. The charges, the excess charges that is, will all go to the outer surface and they will all become evenly spaced. They'll be evenly spaced on the outer surface. Does that make sense? Now, before you write this, I want to draw a little picture here. You see on the right-hand diagram, you see the electric field lines on the outside here. Let's draw the electric field lines on the inside. Field line points toward the negative. Field line points toward the negative. Field line points toward the negative. What do you think, if we did a detailed vector analysis of this, what do you think that those field lines would add up to give me? 0. The net electric field inside a hollow conducting sphere is 0. Contrary to popular belief, that's the reason your car is the safe place to be in a lightning storm. Your car gets struck by lightning, you are perfectly safe. But it's not because of the half-inch of rubber between you and the road. If lightning has the ability to go through several kilometers of air as it goes from the cloud to your car, then it certainly has the ability to go through about 2 centimeters, if that, of rubber in your tires. The rubber tires does not protect you at all, really, in the event of a lightning storm. The voltage, the potential difference is too high. What protects you? The fact that you're inside a conductor. It's not a conducting sphere. It's not as uniform as this, but it's still a conductor. The net electric field inside is 0. Therefore, there's no electrical effect whatsoever inside that conductor. Does that make sense? Last year, my computer died. My desktop computer at my house died. I threw it out, but before I threw it out, I took out the hard drive because there's some stuff that I wanted to get off. Now, I still haven't got anything off of it. I still haven't done anything with the hard drive. But as soon as I took the hard drive out of the computer, this is what I did with it. This is actually it. This is the one. What did I do with it? I wrapped it in foil. Why did I wrap it in foil? Yes, the net electric field inside this foil is 0. You can't shock this. Okay, you can shock it. You can shock the outside of it, but you can't shock the inside. So the hard drive inside, which is normally very sensitive to static discharge, is completely protected by the tinfoil because you can't get an electric field inside a conductor. We call it a Gaussian surface. So, not sure when I'm going to deal with that hard drive, but it doesn't really matter. It's safe. It's not going to get static discharge to it and be destroyed because of that, as long as I want to leave it there.